Hello, 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 and welcome to the Academy of Useless Ideas. Mathematicians have a knack for obsessing over the existence and uniqueness of things. When it comes to limits, uniqueness is a piece of cake, but existence, not so much. Today we are going to dive deep into the necessary and sufficient conditions for the existence of limits of real numbers, which will inevitably lead us to the concept of limit superior and limit inferior. Buckle up, folks, and let's get started. Before we start searching for sufficient conditions for the existence of limits, let's review a necessary condition. The sequence must be bounded. This is easy to check because if xn is a sequence converging to x, then almost all of the elements of the sequence must fall within a ball of radius 1 around x. This implies that the sequence must be lower bounded by the minimum of the values that lie outside of the ball and 1 minus x, and upper bounded by similar reasoning. Interestingly, in the real numbers, the Bolzano-Weierstrass theorem tells us that boundedness is sufficient for the existence of subsequential limits. However, just because a sequence is bounded doesn't guarantee that it converges. There are plenty of bounded sequences that don't converge. Nevertheless, the fact that convergent sequences must be bounded suggests that we should focus on precisely those type of sequences. So let's ask ourselves, is there a type of bounded sequence for which we can ensure the existence of a limit? Let's find out. What about bounded sequences that always grow, or sequences that always plunge? It seems reasonable to conjecture that the limit of such sequences should exist, since they are bounded and can't escape accumulating in one place. But before we make any wild conjectures, let's define what we mean by a growing/plunging sequence. An increasing sequence is a sequence xn, where for every n, x of n plus 1 is larger than x of n. Similarly, a non-increasing sequence is a sequence xn, where for every n, x of n plus 1 is smaller than or equal to x of n. For those with a hyper-analytical mind, this definition can be confusing because a non-increasing sequence is not the same as a sequence that is not increasing. Can you see why? It's a bit of a tricky one, but the disparity in the definition just goes to show that mathematicians can be as irrational as any other human being. Anyways, we can also define decreasing and not decreasing sequences. Finally, a sequence is said to be monotone if it's either non-increasing or non-decreasing. With those definitions out of the way, we are finally ready to state the so-called monotone convergence theorem. Every bounded and monotone sequence of real numbers converges. We'll prove the case of non-decreasing sequences since the other case is similar. Now, since the sequence is not increasing, a natural candidate for the limit is the supremum of the range of the sequence. Let's call that supremum alpha. For any given epsilon greater than 0, there exists an element xn in the interval between alpha minus epsilon and alpha. But since the sequence is non-decreasing, every element of the sequence after xn also lies in that interval. Therefore, alpha is indeed the limit of the sequence. Easy, right? Now that we have the powerful monotone convergence theorem on our side, we are ready to hatch our plan for finding sufficient conditions for the existence of limits. In the real numbers, we know that a bounded sequence converges when all its subsequential limits are the same. But let's be real, that's not exactly a user-friendly condition. It forces us to check infinitely many possible subsequential limits, which is about as much fun as counting grains of sand on a beach. However, if the largest subsequential limit and the smallest one are the same, then every subsequential limit would converge to the same point. So the question becomes, how the heck do we find the largest and the smallest subsequential limits of a sequence? The idea of limit superior and limit inferior is crucial to finding sufficient conditions for the existence of limits. Given a sequence xn, its limit superior, or Limsup, is the largest subsequential limit, while its limit inferior, or liminf, is the smallest subsequential limit. Let's focus on the Limsup for a moment. Consider the sequence -1 to the power of n over n. The sequence converges to 0, but we cannot use the monotone convergence theorem to prove it because the sequence is not monotone. However, we can create a monotone sequence by looking at the supremum of the k-tail of the sequence. The k-tail of a sequence is a subsequence that starts at the kth element and keeps going forward. The sequence of the supremum of the k-tails is monotone because the supremum of a set is larger than or equal to the supremum of any of its subsets. Since the resulting sequence is monotone and bounded, we can find its limit, which is indeed the infimum of the sequence. This is the definition of the Limsup of a sequence. Similarly, we can define the liminf. In summary, the Limsup and liminf provide a way to extract information about the behavior of a sequence, which we will use to determine if the sequence converges or not. With these definitions, we can now show that the liminf and Limsup are indeed bounds for any subsequential limit. Note that every element xn of the sequence lies between the infimum and the supremum of the nth tail of the sequence. Therefore, for a convergent subsequence xnk, we can take limits of the inequalities. The limit on the left converges to the liminf of the sequence, while the limit on the right converges to its Limsup. In other words, any subsequential limit of the sequence must lie between its liminf and Limsup. Next, we turn to the question of whether we can find a convergent subsequence of xn that converges to Limsup. Suppose xn is a sequence with Limsup equal to alpha. As the Limsup is an infimum, we know that for any k, we can find the supremum of the nk plus 1 tail between alpha and alpha plus 1 over k. Let mnk be that supremum. Since mnk is a supremum, we can find an xnk that lies between mnk minus 1 over k and mnk. Therefore, xnk is within a ball of radius 1 over k around alpha. Finally, the subsequence xnk that we constructed in this way converges to alpha. With the concepts of liminf and Limsup, we have a necessary and sufficient condition for the existence of a limit. Specifically, the sequence xn converges if and only if it is bounded and its liminf and Limsup are equal. In other words, the sequence converges if and only if its greatest and least subsequential limits are the same. This provides a useful tool for determining the convergence of a sequence without the need to check an infinitely number of subsequences.